question about this? Yes?
I'm just wondering if the lateral can be removed because
okay. Yes. This side is okay? No? Is it okay that way? No?
Yeah, that's a lot better.
Okay. So, you'll speak. Louder.
Okay. There's no microphone. We would like this course to be quite interactive, so if you have any questions, please do not hesitate to ask or stop me in the middle of everything, so that we can have some discussions. So longitudinal data analysis is an important area in biostatistics, and I think that many of you have used or are going to use longitudinal data analysis. So you use it when you have several observations over time for each subject, but you don't necessarily have the same number of measurements or the same kinds of measurements for each subject. And the general idea is to model individual profiles over time and to model the correlation structure between measurements on the same subject. So we will see two different parts. First, inference on fixed effects, then estimation of variance components, and prediction of random effects. So the linear mixed model can be written like this. So yi equals xi beta plus zi ui plus ei. So these are the classical notations of mixed models. So yi is the vector of observations for individual I at ni time points, so from time t1 to time tni. Xi beta are the fixed effects, so xi is an incidence matrix of dimension ni times p, and beta is the parameters of fixed effects to be estimated. It's of dimension p times 1, and it represents the population parameters, and in particular the average curve in the population. Zi ui represent the random effects for individual I. They represent the individual deviation for subject I from the average curve. And Zi is an incidence matrix of dimension ni times q, and ui are the individual random effects of dimension q times 1. And the residuals, ei, are random measurement error of dimension ni times 1. And ui, so the random effects, and the residuals, ei, are assumed independent and normally distributed with mean 0, and variance covariance g for the random effects, which is at dimension q times q, and ri for the residuals. So ri is of dimension ni times ni. And it follows that the observations yi for individual I are normally distributed with mean xi beta and variance covariance pressure Zij, Zi prime plus Ri. So to obtain estimation of the fixed effects, we maximize the likelihood. So the observations yi are assumed to be normally distributed with mean xi beta and variance covariance vi. So the likelihood can be written like this. So minus 2 log of the likelihood. If you assume that you have n subjects that are independent, you can write that it's the sum for I equal 1 to n of ni, so the number of observations for individual I, times log of 2pi, plus log of the determinant of the covariance matrix, vi, plus the transpose of yi minus xi beta, multiplied by the inverse of the covariance matrix, vi minus 1, n multiplied by yi minus xi beta. So this is the likelihood. And if you calculate the derivatives of this likelihood with respect to parameter beta, you can show that the estimation of beta hat, can be written like this. So it's x prime v minus 1x, v minus 1, multiplied by x prime v minus 1 yi. So this is the classical generalized least square estimator of the fixed effects. Now if you want to calculate the covariance of this estimator, you can see in this expression the only term that is random is yi, the vector of observations. So if you use this formula, variance of ay, where a is a known matrix and y is a random vector, the variance of ay is equal to a variance of y multiplied by the transpose of a. So the variance of beta hat, the estimates of the fixed effects, the variance can be written like this. And the variance of the observations, yi is equal to matrix vi. So you can see that in this expression, this term and this term cancel out. So in total, we get that the variance of beta hat is equal to x prime b minus 1x to the minus 1. So that's how you obtain the variance of the fixed effect estimator. So now if you want to draw inference on the fixed effect, so for each parameter beta j, for j from 1 to p, you have that the standard errors of the estimates beta j hat is equal to the square root of the variance beta j hat that we just calculated before. So if you want to test hypothesis on the fixed effects, you can use the whole test. For example, if you want to test if the beta j parameter is equal to 0 versus beta j different from 0, the test statistic can be written like this. So it's beta j hat, the estimates of beta j minus beta j divided by the standard error of the estimates. And for one test, this test statistics follows asymptotically under the null hypothesis, a normal 0, 1.
Just a question.
Yes?
If you would have just a least squares model, then you would call this a student T.
Well, that's what I'm going to explain afterwards. In the whole test, you assume that the standard error of the estimates beta hat are known. So you assume that you don't estimate the variance of the parameters, and in the t-test you correct for this.
Okay.
And so I'm going to explain it afterwards. Yes?
The whole test isn't the chi-square distributed?
The whole test, well, in this case, it's normal, and in the multivariate case, it's the chi-square. It's the next one here. In this case, when you want to test a contrast like L beta equals 0, so it's a multivariate test with a known contrast matrix L. Then you want to test L beta equals 0 versus L beta different from 0. Then the test statistic can be written like this, and it follows asymptotically under the null hypothesis a chi-square with rank of L degrees of freedom. And I think that in your handout it's written L degrees of freedom, so it's actually the rank of L, the rank of the contrast matrix. But the whole test doesn't take into account variance parameters in matrix VI are estimated, they're assumed to be known, which is not the case. So they underestimate the variability of parameter beta. So to overcome this problem, you have to use t-tests or f-tests. So if you want to test a hypothesis such as beta j equals 0 versus beta j different from 0, the test statistic is still the same. So it's beta j hat minus beta j divided by the standard error of the estimates. And for a t-test, this test statistics follows approximately under the null hypothesis a student distribution with d degrees of freedom. And d is usually estimated in SAS by sideways approach. And similarly, if you want to test a hypothesis such as L beta equals 0 versus L beta different from 0, the test statistics is the same as previously, so it's W hat divided by the rank of L, so the rank of the contrast matrix, and it follows approximately under the null hypothesis a Fisher distribution with rank of L and d degrees of freedom. And this is the F test. So you saw that the inference on parameters beta also depends on the specification of the variance covariance structure, VI. And Liang and Ziegler in 1986 proposed a sandwich estimator for robust inference of the variance of the estimates beta hat. So what they do is that they propose to replace the variance of the observations, yi, by ri multiplied by the transpose of ri. So ri represents here the residuals, which are calculated by the observations yi minus xi beta hat. And this provides a consistent estimator of the variance covariance matrix if the expectation xi beta is correctly specified. But this sandwich estimator is in general not used in SAS, so it's necessary to correctly specify the covariance structure. So also if you want to compare nested models with different fixed effects, for example, if you want to test the null hypothesis is the vector parameters beta in a subspace omega beta 0 of the total parameter space, the likelihood ratio test statistic can be written like this. So it's minus 2 log of the likelihood in the reduced space divided by the likelihood in the complete parameter space. So here, this expression, theta hat ml0 represents the maximum likelihood estimator of the parameters theta in the reduced space, so omega beta 0, and theta hat ml is the maximum likelihood estimator in the complete space, omega beta. And the likelihood ratio test statistic follows asymptotically under the null hypothesis a chi-square with L degrees of freedom, where L is the difference of dimensions between the two spaces, so the global parameter space and the reduced parameter space. So now we've seen inference on the fixed effects. So we are going to see how to estimate the variance components. So you probably know that ML estimators are biased for variance components, and that estimation of variance covariance parameters is usually based on random likelihood. So the random likelihood is defined like this. So minus 2 log of the random likelihood is equal to minus 2 log of the ML likelihood, but corrected for this term, which is the log of the determinant of x prime v minus 1 x. So to estimate the variance components, you usually use iterative algorithms to maximize the likelihood with respect to the variance components. So you can use the EM algorithm, or the Newton-Raphson algorithm, or the Fisher scoring. And the constraints are that the variance covariance matrices have to be semi-definite positive. Now, if you want to compare nested models with different covariance structures, you can also use the likelihood ratio test, as we did for the fifth effect. The problem is that now the null hypothesis is usually on the edge of the parameter space, because, for example, if you want to test that one of the variance components is equal to 0, it's on the edge of the parameter space because the variance parameters always have to be positive. And in this case, the test statistic follows asymptotically under age 0 a mixture of chi-square distributions. In this case, for example, it will be a mixture of chi-squares with 1 and 2 degrees of freedom. So good references for this problem of testing, of test on variance components parameters are Stram and Lee, so the papers from 1994 and 1995, and the book by Verbier and Molenberg in 2000. And you have to note and to be careful that you cannot compare models with different fixed effect structure using the Randall likelihood. You can only compare models with different covariance structure with the Randall likelihood. Otherwise, you have to use the ML likelihood if you want to compare models with different fixed effect structure. So if you want to compare non-nested models, you usually use information criteria. So the idea is to compare models based on their likelihood values, but to penalize for the number of parameters in the model. So the most well-known criteria are IKT, or AIC, which is defined as -2 log of the likelihood plus 2s. So here in your handouts, you'll have to correct that it's plus 2s. Because with this definition here, -2, you want to have the smallest value of the AIC and BIC criterion, so you penalize by adding a term to increase the values. So it's a plus, not a minus in the formula. So IKT is defined like this. So S here is the total number of parameters in the model. And in BIC, so it's -2 log L plus S log of n star. So S is again the total number of parameters in the model. And n star is for the Randall n minus p, where p is the number of fixed effects. N star is equal to n for ML. So there is a little discussion here about the choice of n. So in the previous version of the SAS-Proc mixed, n was the total number of observations, but now it is the number of individuals. Because actually BIC was proposed for independent data, so independent observations, and in the case of longitudinal data, the data are correlated. So I think that there is no clear definition of BIC in the case of longitudinal data. So I think that the exact number to be used for n is something between the two. So it's something between the total number of observations or the number of subjects. But I think there is still some research to do. So probably you have to take into account the correlation structure between the data or something like this. So maybe some of you will work on this during their PhD. So with the information criteria, you cannot use them for formal inference. You cannot use them for significant sets, etc. You saw that BIC penalizes more than AIC for the number of parameters because you multiply by the number of observations. AIC tends to favor over-parameterized models. So in general, when you don't have the same results between BIC and AIC, you usually prefer BIC. So now we'll see how to predict the random effects, UI. So is there any question? So predicting the random effects UI is useful to study deviations for of individual profiles from the mean curve, or to detect outliers, to predict future individual values, and of course in the animal breeding context to predict the genetic values. So you obtain these predictions of the random effects by the block, the best linear and biased predictor, from Henderson's mixed model equations. So they can be written like this. They are very well known by animal breeders. So R here is a block diagonal matrix with Ri on the diagonal, and gamma here is a block diagonal matrix with G on the diagonal. And you obtain the predictions of the random effect here from these equations. You have. So I will give you a few definitions for missing values. Missing values is a very important issue in longitudinal data analysis, and there has been a lot of research in this area. But I will just give you here a few definitions. I will not go too much into details. So the definitions have been proposed by Litton and Rubin in 1987. So they note Y, the data vector, which is composed of the observations and the missing values. N is the missing value indicator, and X are the covariables in the model. So they note F of M given the observations and the missing values, and the covariables X, the conditional probability that an observation is missing. So the missing values are said to be missing completely at random if the missing data are completely independent from the process of interest. So if the missing data do not depend either on the observations or on the missing data or on the covariables. They are said to be covariate dependent if the missing data depend on the covariables that are included in the model. For example, if they depend on the treatment group or sex, etc. And they are said to be missing at random if the missing data depend on the observations. So for example, if the data are missing once the observations drop below a threshold. For example, when the observations become lower than a threshold S. And the last case is the data missing none at random, where the missing data also depend on the non-observed values. So in the three first cases, missing completely at random, and covariate dependent, the missing data are said to be ignorable. So you can use a classical maximization of the likelihood to estimate the parameters. But in the case of missing none at random, then the missing data are said to be informative. And in this case, you have to model the joint distribution of the observations, Y, and of the missing value indicator, M. So this case is quite complicated to deal with. In the examples we are going to study here, we will always assume that the missing values are ignorable. So we will now see the different steps for the model construction for the analysis of longitudinal data. So the model is written like this. We have yi, the observations, equals xi beta plus zi ui plus the residuals ei. So to construct the model, what Verbeek and Molenberg recommend is to choose first to select the fixed effect structure, the xi beta. So in this first step, you will choose the most complete fixed effect structure, as complete as possible, and then you will do the significance tests afterwards. The second step is to choose the random effect structure covariance structure G. Then, to specify the residual covariance structure R. And then you go backwards. You perform significance tests for the G parameters given the choice of the residual covariance structure. And finally, you perform the significance test for the fixed effects that you included in the first step of your model construction, given the covariance structure V. So once you have chosen the random effects and the residual covariance structure. So we will see all these different steps in more detail. So we will illustrate this model construction on an example, which is a facial growth example. It's a very famous example which has been used in many textbooks. So it was originally proposed by Potoff and Roy. We have 27 subjects with 11 girls and 16 boys, and we have 4 measures for each subject at age 8, 10, 12, and 14 years. In total, we have 9 missing observations that are assumed to be missing at random. So the estimation of the parameters can be done directly by SAS/mixte. So there is no need here to remove subject with missing values. So the first step of the model construction is to choose the fixed effect structure. And you want to choose it as complete as possible. So what does it mean? If you have only one effect to study, for example, if you want to study only a treatment effect over time, then you can use the saturated model, which means that you will estimate treatment effect at each measurement time. But if you have many times of measurement, or if you have the continuous covariable, then you will have to use a graphical representation of the individual profiles or a smooth average curve, and you will have to try to find some appropriate parametric function to model this average curve. So in the example that we are studying, for example, here are the individual profiles over time for the first group, or for the girls. So you can see here that the trend is nearly linear. And here are the individual profiles for the second group, for the boys. So it seems also to be nearly linear. But you can maybe assume that the intercepts for the two groups are different, and maybe the slopes in the two groups are different too. So in this first step, we will assume a linear average curve in both groups, and the fixed effects will then be sex. So for the intercept, we will have here a different intercept for the two groups, and the slope, which will be the interaction between sex and age, where age is a continuous variable. And then we will perform the significance tests for the fixed effects after choosing the covariance structure. So the second step of the model construction is to choose the random effect structure. So it's to choose the random regression model. So the random effects represent individual deviations from the mean curve. So to see which will be the most appropriate parametric structure, you have to plot the graph of individual residual profiles. So these residual profiles are calculated as the observations minus the fixed effects, so xi beta hat. Where beta hat here is estimated with an ordinary d-square estimator. So assuming that the data are not correlated. And then you choose from this graph the most appropriate parametric function. So you see that these residuals here correspond to the individual deviations from the mean curve. So it's what remains once you have removed the fixed part. So in the growth example, here is the individual residual profiles over time. So you can see that for most of them the trend is again nearly linear, or maybe even constant. So in this step, we probably choose a linear random regression, and then we will check afterwards if a simple random intercept would be sufficient. So here is how you can write the linear random regression model. So you have here the fixed effect, x, I, j, beta, that we have chosen before. And now the linear random effect, so AI, which means that you will predict for each individual I one random intercept, AI, and here is the slope. So for each individual, you will have one linear curve with parameters AI and BI. And the random effect of AI and BI are assumed to be normally distributed with mean 0 and variance covariance G. And the G matrix is defined like this. It's the variance of A, variance of B, covariance of AB. And the residuals here I assume to be independent with a constant variance. And UI and EI are assumed to be independent. So in this linear model, here is the covariance function between the observations at time tj and tk for individual I. So this covariance is the covariance between all the random terms, so AI plus BI at time tj plus the residual EIJ, and the same thing at time